If I told you that the moon could fit inside the gap between the Earth and its orbit almost 30 times over, would you believe me? Most people wouldn't, because we have spent our whole lives looking at pictures of the solar system that are lying to us. Every textbook diagram, every poster on a classroom wall, every image search result crams the sun and all 8 planets into one tidy little row, close enough to touch. It looks clean. It looks manageable. And it is completely, wildly, almost unbelievably wrong. So I decided to stop looking at pictures and start looking at reality. I took the actual scale of our solar system, shrank it down to a size a human being could walk, drive, and feel, and then I built it across my entire state, planet by planet, mile by mile, until I finally understood something that no textbook ever taught me. Space is not just big. Space is almost entirely empty, and we are floating through nearly all of that emptiness on a rock the size of a grain of sand. This is the story of that project, from the very first calculation on a piece of paper to the final planet placed hundreds of miles from where I started. Stick with me through this, because by the end you will never look at the night sky or a map of your own state the same way again. My scale model actually matters. Before I placed a single model, I had to answer a question that sounds simple but genuinely trips people up. What does scale even mean when we are talking about something as enormous as the solar system? Most diagrams use what is called a logarithmic scale, or they simply ignore distance altogether and space the planets out evenly so they fit on a page. That approach is useful for teaching the order of the planets, but it destroys any sense of proportion. It teaches the wrong lesson. It tells your brain that Mars is just a little farther from the Sun than Earth, and that Neptune is only a bit farther out than that. In reality, the difference between the inner planets and the outer planets is staggering, and the only way to feel that difference is to build something at a true linear scale, where every inch of model distance represents the exact same number of real miles, all the way out. So that is what I set out to do. I picked a single scale and applied it with total consistency from the Sun all the way to the edge of the classical solar system. I decided that my Sun, in this model, would be roughly the size of a basketball, moderately large, so the smaller planets could still be represented with something more than an invisible speck, but small enough that the resulting distances would fit within the length and width of my home state. Once that decision was made, every other measurement fell out of a straightforward ratio. Shrink the Sun down by a certain factor, and every other body in the solar system, along with every gap of empty space between them, shrinks by that exact same factor. I ran the math more than once, because I did not trust myself the first time. The real Sun is about 865,000 miles across. If I shrink that down to the size of a basketball, roughly 9.5 inches, the scale factor works out to something in the neighborhood of 1 to 5.5 billion. That single number became the master key for the entire project. Every planet size, every orbital distance, every gap of nothing between one world and the next, all of it had to obey that same ratio. Placing the Sun the morning I placed the Sun, I drove to a public park near the edge of my city, the kind of place with wide open lawns and a walking path that loops around a small lake. I set up a tripod, mounted a basketball on a low stand, and stood back to look at it. It felt almost silly at first, a basketball on a stick in the middle of a park, but I reminded myself what that basketball represented. Every scrap of light and heat that has ever touched this planet came from something like that ball, except 32 million times more massive than the entire mass of Earth. 99.8% of everything in our solar system, by mass, is contained in that one glowing sphere. Every planet, moon, asteroid, and comet put together makes up less than a rounding error next to the Sun. I filmed that first shot for a long time, longer than I needed for the final cut, because something about standing next to that basketball made the scale of the real Sun finally click for me in a way that no photograph ever had. This was going to be my 0 point. Every other location in this project would be measured outward from this single park bench. Mercury, the scorched messenger. The first stop was Mercury, and honestly, it was almost anticlimactic. At my chosen scale, Mercury sits only about 650 feet from the Sun, which in the real solar system corresponds to 36 million miles. 650 feet is not even a quarter of a mile. I could see my basketball sun from Mercury's position without any real effort, just a short, easy walk across the same park. I placed a small sphere there, barely larger than a peppercorn, to represent Mercury, a scorched, airless world that swings so close to the sun that its surface temperature can climb past 800 degrees Fahrenheit during the day, then plunge to nearly 300 degrees below zero at night, because it has essentially no atmosphere to hold onto any heat. Mercury takes just 88 days to complete an orbit, the shortest year of any planet, and yet a single day on Mercury, from sunrise to sunrise, lasts an astonishing 176 Earth days, because of the strange, slow way the planet rotates relative to its orbit. Standing there with my tiny peppercorn planet in hand, so close to the towering basketball sun, I understood in my gut why Mercury has no real chance of holding water or air. It is simply too close to the fire, Venus and the furnace beneath the clouds from Mercury. The walk to Venus was longer but still comfortable, taking me to a spot roughly 1,200 feet from the Sun, corresponding to Venus's real distance of 67 million miles. I used a slightly larger marble for Venus, since in reality it is almost the same size as Earth, just a touch smaller. Venus fascinates me because it breaks people's intuition. It is farther from the Sun than Mercury, and yet it is the hottest planet in our entire solar system, hotter even than Mercury, with surface temperatures around 860 degrees Fahrenheit, hot enough to melt lead. The reason is its atmosphere, a crushing blanket of carbon dioxide roughly 90 times denser than our own, wrapped in clouds of sulfuric acid, trapping heat in a runaway greenhouse effect. Standing at the Venus marker, I found myself thinking about how easily a planet's fate can turn on the composition of a thin shell of gas above its surface, and how that same lesson applies a little closer to home than we might like to admit. Earth, the blue marble in an empty room. The walk to Earth's position took me out of the park entirely and onto a paved trail that ran alongside a road, roughly 1,660 feet from the Sun in total, corresponding to the true distance of 93 million miles, the measurement scientists call one astronomical unit. I placed a small blue and green marble there, about the size of a pea, to represent our entire world. Every human who has ever lived, every ocean, every mountain range, every war and celebration and quiet afternoon, all of it happened on that pea-sized marble. Off to one side, only about 4 inches away from the Earth marker, I placed an even smaller model to represent the Moon, a speck barely larger than a grain of sand. That 4-inch gap represents roughly 239,000 real miles, and it always surprises people how close, relatively speaking, the Moon actually sits to us compared to the emptiness that follows. Because after Earth, something strange starts to happen to the landscape of this project. The gaps begin to grow enormous, the long, empty walk to Mars. Getting to Mars meant driving, not walking. At true scale, Mars sits about 2,530 feet from the Sun, just shy of half a mile, corresponding to a real distance of 142 million miles. I placed a small rust-colored bead to represent the red planet, a world about half the size of Earth, with a thin, wispy atmosphere mostly made of carbon dioxide, polar ice caps of frozen water and carbon dioxide, and the largest known volcano in the solar system, Olympus Mons, which rises nearly 3 times the height of Mount Everest. Mars holds a special place in modern space exploration because it is the leading candidate for future human missions beyond the Moon, thanks to its accessible surface, its day length remarkably close to our own at just over 24.5 hours, and growing evidence of ancient water that once carved river valleys and lake beds into its now dry, dusty surface. Placing that bead down and stepping back to look at the empty stretch of road between it and Earth's pea-sized marble gave me the first real jolt of the entire project. This was already close to half a mile of essentially nothing, and I was still nowhere near finished with even the inner solar system. Crossing the asteroid belt. Between Mars and Jupiter lies the asteroid belt, and I wanted to represent it honestly rather than skip over it as an afterthought. At true scale, this belt spans a wide band starting around 3,500 feet from the Sun and stretching out towards 6,000 feet, corresponding to roughly 200 to 300 million real miles from the Sun. I scattered a handful of tiny grains of sand and small pebbles across that stretch of my route, representing bodies like Ceres, the largest object in the belt and technically classified as a dwarf planet, along with Vesta, Pallas, and countless smaller fragments left over from the early solar system's formation. Here is something that genuinely surprised me when I researched it, and I suspect it will surprise you too. Despite what science fiction movies show us, the asteroid belt is not a dense, chaotic minefield of rocks that a spacecraft has to dodge and weave through. It is almost entirely empty space, with the total mass of everything in the belt adding up to less than 4% of our own moon's mass, spread across a region of space so vast that spacecraft have flown through it multiple times without ever needing to dodge a single object. My little scattering of pebbles along the roadside represented that truth perfectly. Presence without density, matter without crowding. Jupiter, the giant that changes everything. After the asteroid belt, the drive to Jupiter took me across a huge stretch of my state, arriving at a point roughly 8,600 feet from the Sun, well over 1.5 miles, corresponding to Jupiter's true distance of 484 million miles. Here I placed a model about the size of a golf ball, since Jupiter is so enormous that more than 1,300 Earths could fit inside its volume, and it has a mass greater than all the other planets in our solar system combined. Jupiter is a world without a solid surface in any traditional sense, a churning ball of hydrogen and helium topped with colorful bands of clouds and storms, the largest and most famous being the Great Red Spot, a storm system wider than Earth itself that has been raging for at least a few hundred years. Jupiter also acts as something like a cosmic bodyguard, its immense gravity capturing or flinging away many comets and asteroids that might otherwise threaten the inner solar system, including the famous impact of comet Shoemaker-Levy 9 in 1994, which slammed directly into Jupiter's atmosphere and left dark scars larger than Earth for months afterward. Standing at the golf ball marker, looking back toward the pea-sized Earth I could no longer see at all, I felt the true weight of what gas giant really means. Saturn and its impossible rings. Continuing outward, I reached Saturn's position at roughly 15,800 feet from the Sun, nearly 3 miles, corresponding to a true distance of about 886 million miles. Saturn earned a slightly smaller golf ball-sized model, since it is a bit smaller than Jupiter but still colossal compared to any of the rocky inner worlds, and I surrounded it with a delicate paper ring to represent its famous ring system. Those rings are made almost entirely of countless particles of water ice, ranging from grains as small as dust up to chunks the size of a house, spread out in a disk so wide it would stretch most of the way from Earth to the Moon if placed here, yet so thin that in true proportion it would be thinner than a sheet of paper relative to its width. Saturn is also the least dense planet in our solar system, so much so that if you could somehow find a bathtub large enough, Saturn would actually float in water. Standing nearly 3 miles from my basketball sun, with a paper-thin ring glinting in the wind, I began to understand why the outer solar system feels like an entirely different universe from the one closer to home. Uranus, the planet tipped on its side. The drive to Uranus stretched the project to roughly 31,700 feet from the Sun, about 6 miles, corresponding to its true distance of nearly 1.8 billion miles. I placed a small pale blue-green marble there, slightly larger than Earth's model but noticeably smaller than the 2 gas giants before it, since Uranus and Neptune belong to their own category, sometimes called ice giants, made largely of water, ammonia and methane ices surrounding a rocky core. Uranus holds a genuinely strange distinction among the planets. It rotates almost completely on its side, tilted at about 98 degrees relative to its orbit, likely the result of a massive collision billions of years ago. That means Uranus essentially rolls around the Sun like a ball instead of spinning like a top, giving it seasons that last around 21 years each, with some regions plunged into decades of continuous darkness while others bake in decades of continuous sunlight. Placing that marble 6 miles from the Sun, further than most people ever drive on a casual afternoon, made the phrase distant planet feel less like a poetic description and more like a literal fact I was standing inside of. Neptune, the windiest world. The final classical planet, Neptune, sat at roughly 49,500 feet from the Sun, close to 9.5 miles away, corresponding to its true distance of about 2.8 billion miles. I placed a deep blue marble there, similar in size to Uranus, to represent the most distant of the 8 recognized planets. Neptune is famous for hosting the fastest winds ever recorded in our solar system, with storms clocked at over 1,200 miles per hour, more than 1.5 times the speed of sound here on Earth. It takes Neptune about 165 Earth years to complete a single orbit around the Sun, which means that since its discovery in 1846, Neptune has only just recently completed its first full orbit since humans first identified it as a planet. Standing 9.5 miles from my basketball sun, I realized I had driven farther to place this one small marble than some people drive in an entire week, and this was still considered part of the main solar system. Pluto and the true Ed. I could not resist adding one more stop, even though it falls outside the strict 8-planet definition. Pluto, reclassified as a dwarf planet in 2006, sits at an average distance that at true scale placed my final marker at roughly 65,000 feet from the Sun, about 12.5 miles away, corresponding to its real average distance of nearly 3.7 billion miles, though its elliptical orbit means that distance actually varies significantly over its 248-year orbital period. I used a grain of sand smaller than the head of a pin for Pluto's model, a tiny, icy, mountainous world with a heart-shaped glacier of nitrogen ice, first explored up close only in 2015 by NASA's New Horizons spacecraft after a 9.5-year journey. Standing 12.5 miles from where I had started that morning with a basketball on a tripod, looking at a speck of sand representing an entire world, I felt something I can only describe as quiet vertigo. This entire drive, this entire day, and I still had not reached the true edge of our solar system. Beyond the model, into the real emptiness. To close out the project, I wanted to give a sense of what lies even farther out, even if I could not physically place a model there. The Oort Cloud, a theorized shell of icy debris believed to surround the solar system, would sit at a scaled distance of somewhere between 300 and 3,000 miles from my basketball sun, meaning it could stretch clear across my entire state and well into neighboring ones. And the nearest star system to our own, Alpha Centauri, at true scale using my model's ratio, would sit roughly 8,000 miles away, nearly a third of the way around the entire planet Earth, just to represent our single nearest stellar neighbor. That is the number that stopped me in my tracks more than any other measurement in this entire project. An entire day of driving, nearly 13 miles, only got me to the edge of the classical planets, and the nearest star beyond our own sun would require a scaled journey equivalent to circling almost a third of the globe. Space is not just big. Space redefines what big even means. What this project actually taught me. When I started this, I expected to learn about distances and numbers. What I actually learned was something closer to humility. Every planet I placed, from tiny Mercury to windswept Neptune, sat surrounded by miles upon miles of nothing, empty road, empty fields, empty sky. Earth's little pea-sized marble, sitting alone at its short distance from the basketball sun, suddenly felt less like the center of the universe and more like a single, improbable point of noise in an overwhelming, silent void. If you ever get the chance, even a simplified version of this exercise is worth trying in your own town. Pick a scale, place a basketball, and start walking. You will feel something that no photograph, no simulation, and no textbook diagram has ever fully managed to capture: the genuine, physical, almost dizzying scale of the solar system we call home. Thank you for walking, driving, and exploring this entire journey with me today. If this kind of deep, grounded look at our solar system is something you want more of, make sure you are subscribed, because there is a lot more space left to explore.